less spectral resolution and vice versa. So that's our problem. So because of that problem, what will happen is that, when you have this, you can see here, this area will correspond to 1 pixel. This area is having only soil. So that 1 pixel will be only soil. Right? There is no problem. But this area contains both vegetation as well as soil. So that 1 pixel will contain both vegetation and soil. So that means here we have seen the spectra. So you will get one spectra which is called a mixed spectra. It's not a pure spectra, it will be mixed spectra of both soil and vegetation. So this problem is called spectral mixing problem. When you have coarse spatial resolution, I told you when you want high spectral resolution, your spatial resolution will be coarse. So what will happen is that you will have this type of mixing, which is called spectral mixing. That means the spectra from here, I hope all of you understood what is spectra. So the spectra from vegetation will be mixing with the spectra from the soil. I hope all of you understood what I mean by spectra. Spectra means it's how this particular material or this particular pixel and the material covering this particular pixel is reflecting across all the wavelengths. So that's the spectra. So this spectra will be different for wheat, will be different for barley, will be different for soil. But the problem is, if you have more than one such thing in your field of view, then there will be something called spectral mixing will happen. So this is a problem that we have to address. So you will have only one value. From that you have to identify what percentage of material 1 is there, what percentage of material 2 is there. So that said, if I get one spectra here, I have to understand how much percentage of vegetation is here, how much percentage of soil is here. See, this is called linear mixing. Okay. I'll tell you, this what will happen is that, I have two objects within this pixel. So within this pixel, I have two materials. One is soil, one is vegetation. So the energy or the rays from the sun is coming here. It is hitting one material. It will go back to the sensor. Then no problem. So that particular material will be recorded for that particular area. But if suppose we have two materials in the same pixel, what will have pixel area? So what will happen? The reflected rays from material 1 and material 2 will travel through the atmosphere, and by the time they will reach sensor, both of them will be mixing together as one. So this is called spectral mixing. So that means you have the reflected rays from material 1, the reflected rays from material 2. Since I have more than one material in that instantaneous field of view, both of these will be getting together or combining together and being received at this sensor. So that means I have alpha 1 into the reflectance of material 1 plus alpha 2 into the reflectance of material 2. They are combining together to give me one spectra which is being received at this sensor. So this is called linear mixing. So that means 1 plus 1. Okay. Linear and non-linear equations we all know. See, x1 plus x2 is a linear equation. x1 x2 plus x2 square is a non-linear equation. Right? So that means x1, let x1 be the reflectance of this material 1, x2 be the reflectance spectra of material 2, then alpha 1 x1 plus alpha 2 x2 will give you the mixed spectra. That's called linear mixing. But what will happen if the materials are very fine? If I will take some minerals, I'll take minerals. If I will take some different rocks, I'll powder them, I'll mix them together. This is called an intimate mixture. So what will happen in intimate mixtures is that, the mixtures are very close, the particles are very close by. So what will happen? First the sun ray or the light will hit on one material, See, if it will directly go to the sensor, there is no problem. But what will happen? This will hit on one material, will hit on another material, will hit on another material, then it will go back to the spectrum. So their problem happens. What is there? So there it will be spectra of material 1 into spectra of material 2 into spectra of material 3 will be going there. So there, the picking is happening at multiple materials, so it's like a non-linear mixing. So there are two things: linear mixing, which happens for macroscopic mixtures. Macroscopic mixtures means which are not very which are actually large objects, the vegetation and soil. But if you consider minerals, it's microscopic mixing. We are doing one project on mapping the minerals on lunar surface using Chandrayaan 2, Chandrayaan 1 and Chandrayaan 3 also we are getting. So all these data. So what is the problem there? These are the minerals there. So minerals, these are intimate mixtures. So what will happen is that this will have a non-linear mixing. So see, this is just a problem. So we have to unmix that. So these are some of the research problems that I was planning to explain here. We don't, because of the limitation of time, we don't know how much we'll be able to cover, but this is one problem that we are trying to resolve. That means, I told you one main problem is the resolution trade-off. You cannot have an image with high spatial and high spectral resolution together. So how you can solve that problem? So this problem, to solve this problem, one solution is to lower the altitude of the sensors. That means you use UAVs. So, but that is I'll just finish it. This in 5 minutes and we can go. Sorry for keeping you waiting. I don't want to repeat this again. So, see this. So one possible approach is that this. So people may ask why you cannot use UAVs, or why you cannot bring the camera down from the satellite, why you are keeping it very high, why you cannot bring them down. You can keep one camera for each places and take the images. What is the problem? It's same like asking why you cannot have electric poles, why you want the unwired network, satellite communication. We are using satellites for communication. You can also use satellites, without satellites you can just have a wired network to have your communication, phone communication, right? Earlier we were having wired networks. Why you need satellite communication? Because it will give you a bird's eye view of the things. And also it's more economical. It's not feasible to always have a drone flying over this area. That the feasibility is a problem. Another thing is it will give you a wide area view of that. So these two are the aspects which demand the use of Earth observation satellites or remote sensing satellites, which takes a photograph of the Earth surface. So now my problem is that I cannot have both high spatial resolution and high spectral resolution images. So either I have to take a hyperspectral image which is having high spectral resolution, and I have to enhance its spatial resolution. See, I have to take a hyperspectral image, an image having many bands, maybe 400 bands, 300 bands, and I have to improve its spatial resolution. Improving spatial resolution means what? You have to break that pixels into small sub-pixels. You can see here, this image was having a coarse spatial resolution. This image is having an improved spatial resolution. What is happening here? One pixel here is now broken down into many sub-pixels. And you have only this value, but using machine learning or using other techniques, you have to find out what are the value for all these individual pixels. So this is an imposed problem that we want to solve. That's where one part of our research problem is that we need to address, we need to take a high spectral resolution image and want to improve its spatial resolution. So that is where we try to use something called the usual approach of using this And there are some data sets which you can go through the slides. These are some of the available data sets. These are openly available. So this is our idea. If I get a coarse spatial resolution image, can I increase its spatial resolution? So, okay, so let's, before breaking for tea, just one thing, sparse coding. What is sparse coding? Suppose I told you already, suppose I have some base vectors, then I can express my actual vectors in terms of those base vectors. Suppose my base vectors are v1, v2, v3, and I have my actual vectors, say I1, I2, I3 up to I100. So that said, I can express I1 as alpha 1 v1 plus alpha 2 v2 plus alpha 3 v3, I2 as beta 1 v1 plus beta 2 v2 plus beta 3 v3. All these I can do in terms of these base vectors. So that base vectors are called dictionaries, and the coefficients alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 are called coefficients. So I have dictionaries, I have coefficients, so I can get that actual data. What is my actual data? My actual data is, say, V1 is my actual data. So V1 I can get by alpha 1 V1 plus alpha 2 V2 plus alpha 3 V2. So this you can correlate with what we have learned in our frequency, Fourier transform and all these things. What we have learned in Fourier transform, see there we were using the Fourier bases as the base vectors. That means the Fourier bases were the base vectors you can see here, these were the base vectors, right? The same way here, what are our base vectors? You have certain base vectors and you have the coefficients that you can combine together to form your data. So that means if I want to get a signal, these f1, f2, f3 are the base vectors and that their amplitude or their strength, alpha 1, alpha 2, alpha 3 are the coefficients. So Fourier transform can also be considered as a way of sparse coding or dictionaries and sparse codes. Same way wavelet, same way we will also see how machine learning can serve as a base for learnable bases. See, these bases are computed. For example, Fourier bases, I am computing the bases using Fourier transform. Wavelet, I am using wavelet transform to compute the bases. Same way you can use any such transform. But certain transforms are fit for certain type of data. Certain transforms are not fit for certain other type of data. So can you learn those bases? So that is where machine learning will come into picture. And so there we will take a break. So only thing is, I just show you that figure and we will wait for the tea. See, this is how, these are the sparse coefficients and you have, your dictionary. So this will become more clear here. This will be one data. So that means this is one image which I am trying to flatten that image. Flatten image means image is now in as a matrix. So can I resize it like a one-dimensional array? If I have a matrix means what? It's having rows and columns. So what I will do, I take the first row, keep it like this, and take the second row, append that second row to the first row, then append it again. So that means now I have flattened this entire image as a one-dimensional array of a matrix. This is called, and row major, appending, or row major way of resizing that array into a 1D, resizing that matrix into a 1D array. So that means I took one row, I placed that row, I appended to the next row. So this way I created one image in a 1D form. So I have these images, these are the dictionaries, these are the sparse codes which will combine together too. So that means if you see like this, this will become more clear. So you can see that there are different images. See, this is 3, this is 8, this is 9, but these are the bases. So these bases can in some way combine together to form 3, some way combine together to form 8, some way combine together to form 9. So coming back to our mathematical correlation, you can easily correlate now this where that small portions of the image that we have seen D, and alpha is how they are combining together. Y may be 8, maybe 3, maybe 1, maybe 2. All these actual data is Y, and all these components can combine together to form these, So these are the bases, these are the actual your data. So we break here for the key. Thank you.
Please edit each basis.
This is